Hello everyone, welcome back to this course for one final time because this is going to be the last lecture on this MOOCs course on principles of mechanical measurement. Now, like I mentioned in the previous lecture, this week we are going to discuss about a few special topics instead of focusing on any particular parameter, or I should say discussing the measuring options of any particular parameter. Like in the previous lecture, I have briefly discussed about acoustic measurements, just to give an overview of that, different parameters associated with acoustic measurements, and also common options like microphones etc. for measuring acoustic signals. Similarly, in today's lecture, I shall also be discussing about one very relevant topic, and again giving only a very brief overview on that, mostly discussing different terminologies and several associated factors with that, and that is radioactivity or radioactive emissions. You know that this is a very hot topic for discussion in the field of energy generation, or I should say nuclear energy generation, and also very much relevant in the day to day life or our day to day activities, because we are always exposed to certain kind of radioactive emissions coming from all possible sources from surrounding us. Particularly, everyone talks about the radiation coming from the mobile screens or the use of electronic devices or corresponding screens that we keep on using, and therefore, I thought about adding a brief discussion on radioactivity and radioactive emissions, mostly focusing on different units or measurement units associated with radioactivity, and also possible health hazards which may get caused by different kinds of radioactive emissions, and try to quantify them in terms of the parameters that we are going to talk today. I would try to keep it only to an overview, discussing very briefly on each of the relevant topic. And for the first term that I have here towards this is radioactivity itself. All of you may have some idea about this particular term, that is radioactivity, and you may be knowing that radioactivity can be defined as a spontaneous disintegration or decay of an unstable nucleus. Here this spontaneous term is very important. Here we are talking about the nucleus decaying or disintegrating into some smaller nucleus or so, and ejecting also a few other particles all by itself, and not being subjected to some kind of external influence. So, the term spontaneous disintegration is the one that characterizes radioactivity, and it also separates it out from different kinds of other possible nuclear reactions. And radioactive decay of an unstable nucleus is always characterized by the emission of particles and or electromagnetic waves, and generally accompanied by the release of huge amount of energy. I am not going to the detailed of the energy production, but just to give you an overview, or I am sure all of you know that whenever a particle goes for such kind of radioactive decay, then if I show you a picture like this, an unstable nucleus or radioactive atom, often called a radionuclei, that goes through some kind of spontaneous decay producing particles, generally more than one number of particles having smaller nucleus, and also releasing energy. This one is known as the parent nucleus, and the products from there, they are known as daughter nucleus. Now, quite often the total mass of the daughter nuclei and also the combined mass of all the particles that are ejected during a radioactive decay is less than the total mass of the parent nucleus itself. And the difference in that mass, though that may be an extremely small number from our real life point of view, but following the theory of relativity, that can lead to the formation of huge amount of energy, or I should say the mass gets converted to energy, and the magnitude of that energy can be estimated using E equal to mc square. So, C being a large number, a very small value of m can often lead to huge amount of energy production, and that is a fundamental principle of nuclear energy production. So, any kind of radioactive decay of an unstable nuclei is always associated with the release of energy and also the production of smaller nucleus or daughter nucleus of smaller size, and ejection of electromagnetic waves and a few other particles. The daughter nucleus itself can also be radioactive in nature, leading to further radioactive decay and thereby formation of radioactive chains till the appearance of some stable daughter nucleus. Now, if you think about the periodic table, then the particles which is having large atomic number, generally we talk about atomic number of 82 onwards. Atomic number means number of protons that is present inside a nucleus. So, when we are talking about a nucleus having an atomic number of 82 or higher, generally most of those nucleus are unstable in nature. 82 is for lead. So, but not all the isotopes of leads are radioactive, but some of the isotopes of lead, bismuth is having an atomic number of 83, they are unstables, and from 84 onwards almost all the nucleus are unstable. So, they can go for radioactive decay. So, our focus is primarily on this energy which is getting released during a radioactive emission, and therefore, whenever you are talking about any kind of radioactive energy emission, we are talking about atoms or nucleus having very high atomic number, generally greater than 82 or greater than 81. Now, radioactive decay can be of several kinds. This is one of the most common kind of radioactive decay, where here it refers to the parent nucleus. Here A is the atomic number, Z is the mass number. Now, what is mass number? It refers to the number of protons plus number of neutrons present inside the nucleus, or together they are called the number of nucleons present inside this, or sorry, here A is the mass number and Z is the atomic number. Therefore, we can also write this one as Z plus number of nucleus. Like for example, if we take a symbol, this is generally the common way we write this. We write something like 8O16, that refers to an oxygen nucleus having atomic number of 8 and a mass number of 16. Therefore, the number of protons, if m we refer to number, then that will be equal to 8, and number of neutron in this will be 16 minus 8, that is equal to 8. So, this is a common way we represent any kind of nucleus, and whenever a radioactive nucleus undergoes this particular decay, it leads to the production of an helium isotope. This helium particle is often called an alpha particle, and therefore, this particular radioactive decay is called alpha decay. So, this is the representation of this. AM is American. So, an American nucleus having a mass number of 241 leads to an alpha, goes for an alpha decay, producing neptunium having mass number of 237 and atomic number 2 less than American. There is another kind of very popular radioactive nucleus, a very common radioactive nucleus is that of beta decay, where actually there is a production of one electron. Electron is designated as -1 is 0 because it does not have mass, or its mass is negligible, but it has a 1 unit of negative charge. So, like here H3 or tritium hydrogen 3 isotope going for an electron decay, or often called the beta decay, producing helium 3 isotope. This is another kind of radioactive emission called the gamma decay, which where gamma is only an electromagnetic radiation. So, there is no change in the atomic or mass number of the isotope, or I should say the parent and daughter isotope are having the same atomic number and mass numbers, but there is at a lower energy level because the excess energy of this parent is being released in the form of this gamma radiation. So, these are some common type of radioactive decay that we generally identify. There can be several other kinds of radioactive decay possible, but there is no need for us to go for any further discussion into this, as our interest is mostly on the energy produced during radioactivity. So, this particular one is of large interest to us, and even the helium or alpha decay is also important because this is generally a heavier isotope, therefore, can carry lots of or large amount of kinetic energy with it. Now, in a radioactive sample, the probability of disintegration is the same for each of the nucleus, and that is generally found to be proportional to the total number of nucleus present in the sample at a particular instant. Therefore, if n is the total number of nucleus present in a particular sample, then the probability of the disintegration, that is the rate at which the number of nucleus is going to change, this dn dt is proportional to the number of nucleus n itself, or introducing a constant of proportionality, we have dn dt equal to minus lambda n. Here lambda is called the decay constant, and this minus sign is coming because the number of nucleus or n is decreasing. We can easily solve this one, that is over a particular period of time. If we solve this, or before that, this is the thing that we are talking about. If suppose initial number of nucleus is 100, then with time it keeps on decreasing continuously following this particular nature. and corresponding mathematical equation after solving this is a form like this, which you can easily obtained by performing an integration, something like minus lambda n dt, integrating this over time t equal to 0 to some t. At t equal to 0, n 0 is the number of nucleus, and n from t, which gives to this particular equation an exponential profile. So, we can get the number of nucleus is exponentially decreasing, and it can become 0 only after infinite period of time, but depending on the value of lambda, it can decrease very quickly. Quite often the term, or from energy use point of view, the term we are more interested in is called activity. Activity is nothing but this rate of decay, that is this particular thing itself. So, or the minus of that as the number of nucleus is decreasing always. So, A is equal to minus d n dt is equal to lambda n, and by combining with this equation, so we can also write this as A equal to A naught into to the power minus lambda t, where A naught is the initial activity, that is the rate of disintegration at t equal to 0. This activity is the one that we are most interested in, because for most of the known radionuclei we generally know what kind of radioactive reaction it undergoes, and therefore, we know that what kind of emission we can expect from a nucleus, whether it will be gamma radiation or alpha radiation or beta radiation. Now, our job is to know total number of disintegration that is going on over a particular period of time, and once we know that, then we can easily calculate the total amount of energy release, because we already know the nature of each of such releases. So, we have to know the activity while for judging the radioactive nature, or I should say the radioactive effect that a particular nucleus can produce. Another parameter that is of very much importance here is half life. Half life is the amount of defined as the amount of time required to reduce the total number of radioisotopes present in a particular sample to half of its original value. Like look at the curve that I have shown here. Initial number of isotopes was 100. So, the at time t equal to 0, and half of that is 50. So, the time it takes to reach this half value, like if we go for the first sample, the red colored one, then it is somewhere here. So, it is reaching half life somewhere here for this. So, this particular period is the half life for that particular red colored sample. Whereas, a particle which is having higher value of lambda, see here, this half life will be this one for the blue colored sample, and it is definitely much smaller compared to this. Now, how can we estimate the value of the half life? Here, going back to this equation, if we put n t is equal to n naught by 2, then what we have? N naught by 2 is equal to n naught into to the power minus lambda into T h or T half, which gives us this particular equation. That is, if we solve this, then e to the power lambda T h is equal to 2, that is lambda T h is equal to log of 2, which gives T h equal to log of 2 upon lambda, or 0.693 upon lambda. So, the half life is inversely proportional to the decay constant, which is very much logical. If the decay rate is higher, half life will be smaller, lesser time will be taken to reach to that half mark, half n mark. Now, our interest now goes back to this A, and the units of radioactivity are defined in terms of this A, the activity. So, the most common, or the standard SI unit, or I should not say SI unit, the most commonly used unit for radioactivity is Curie, based upon definitely the name of the first person who properly formulated the theory of radioactivity, even coined the term radioactivity as well, the Curie family, or Pierre Curie and Madame Curie. Now, 1 Curie corresponds to the activity of 1 gram of radium 226, which generally comes to be 3.7 into 10 to the 10 number of disintegrations per second. So, this particular radium sample, the 1 gram of radium sample, that number of disintegrations or radioactive decay it undergoes in 1 second of time, that is defined as 1 Curie. But it is usually a very large number to deal with. So, quite often the lesser unit, or the SI unit of radioactivity is Becquerel. Becquerel, actually Henry Becquerel is actually the first person who observed this phenomenon of radioactivity, but failed to understand the underlying physics for this, which was later explored by Curie family. So, becquerel is the SI unit of radioactivity. It is also a measure of the quantity of radioactive material. 1 becquerel is just 1 disintegrations per second. Therefore, 1 Curie is actually 3.7 into 10 to the power 10 number of becquerels, or as shown here, 1 becquerel is 1 by 3.7 into 10 to the power minus 10 Curie, or 2.703 into 10 to the power minus 11 Curie. So, these are SI units of radioactivity, based upon which we measure the potential of any radioactive elements. And whenever we are talking about radioactive decay, not from only in nuclear isotopes, but even from any other sources also, generally these are the units in terms of which we measure the same. And this is the instrument which is most commonly used for measurement of radioactivity. It is called the Geiger-Müller counter. Now, just look at the picture that I am given here. It consists of a cylindrical chamber like shown here, with a wire stretched along its longitudinal axis. Now, this is the wire that I am talking about. You have a wire stretched along the longitudinal axis, the cylinder wall acts as the cathode and the wire as the anode. The positive voltage is applied to the wire, so it can act as the anode, whereas the wall is connected to some negative terminal. So, the wall is the cathode in this case. Now, the cylinder is filled with some kind of inert gas maintained at a very low pressure, can be helium, neon, or even nitrogen also. Occasionally it can is mixed with ethyl alcohol to increase the sensitivity of the instrument. Now, when an ionizing particle, something like a photon or any other kind of energy ionized particle that passes through this gas, it becomes conductive due to ionization for a very brief period, which can be sensed with the corresponding circuitry. This ionization is substantially amplified by this the electronic circuitry to produce a detectable pulse. This pulse is sensed by the processing unit, which is here, and accordingly it provides a measure for the activity. That is, over a particular period of time, the total number of pulse it has recorded. Say if this is the pulse, then the number of pulse divided by the time is definitely going to be the radioactivity, the activity of that particular sample. It is the advantage of this particular counter is it is a robust structure, and it is not very costly. It is relatively cheap, quite proven technology, and easily available. Limitations is it is unable to it can't differentiate between the radioactive radiation types, that is whether the radiation is coming from alpha rays or gamma rays. It is not able to distinguish, as the output pulse is insensitive to the energy of the incident radiation. It can just sense whether there is energy coming in or not, but what is the magnitude of energy, what is the characteristic or source of that energy, it does not give any idea. Also, owing to its own date time, that is the time it takes between two the minimum time it requires between two successive readings, because of that it also can't measure very high rate of radiation. Still, this particular counter is the most common device for measurement of radiation, or particularly nuclear radiation. Now, the one that we are more concerned nowadays about is the health hazard caused by the radiation. And whenever you are talking about the health hazard that can be the result of any kind of radioactive emission, then just the units of Curie or becquerel are not sufficient. Rather, we have to identify some other unit which can relate the radioactivity in terms of the health hazards or health effects. The magnitude of radiation exposure a living person or any other matter is subjected to is commonly expressed in terms of the radiation dose. So, radiation dose refers to the radiation exposure one human being or something else, generally characterized in terms of human being only, the magnitude of radiation it is exposed to, that is the radiation dose, and there are three kinds of definitions of this radiation dose. First is Roentgen. Have you heard the name Roentgen? He is the inventor of X-ray, which is originally used to be called the Roentgen ray or Roentgen ray, but now it is more popularly called the X-ray, because that is the name that he used. Now, Roentgen is an unit which is the amount of exposure energy produced by gamma or X-rays in a cubic centimeter of dry air at STP. Just look at the definition properly. We are giving a particular volume, that is 1 cubic centimeter of dry air at standard temperature and pressure. So, we are talking about a given volume, given pressure, temperature. So, we are talking about a particular mass of dry air, means no moisture present there, then the amount of energy or exposure produced by gamma or X rays in that is a measure of Roentgen. Second is RAD or radiation absorbed dose. RAD is the short form, radiation absorbed dose. It is a measure of the absorbed dose, which is the amount of energy deposited in a unit mass of human tissue or other media. So, 1 rad corresponds to 100 arc per gram or 0.01 joule per kg. That is, if I provide you 1 kg of human tissue and because of this radiation 0.01 joule amount of energy is being deposited into that, means the total energy content of that 1 kg of human tissue increases by 0.01 joule, then that the corresponding physical dose or absorbed dose is called RAD, radiation absorbed dose. And then add in there, the next one is REM, Roentgen equivalent mean or Roentgen equivalent man. It is a measure of the biological equivalent dose, which amounts to the biological damage caused by irradiation, considering the amount of total energy deposited and also the rate of energy loss per unit distance traversed by the particle. The response to different organs of our body are different against the same radiation, and therefore, we also have to take into consideration how much biological damage this irradiation is causing. And that will depend upon the total amount of time the radiation is allowed to total amount of energy that is getting, definitely total amount of energy that is getting deposited on the tissue, and secondly the rate at which rate of energy loss per unit distance traversed by the particle within the tissue. These two combined generally is given in terms of something known as quality factor, this QF. Different particles has different kinds of quality factors, like X-ray, gamma rays or the beta particles. They are generally very light, very low mass, or like X-rays and gamma rays are electromagnetic radiations or electromagnetic waves, and therefore, they does not have any mass. Beta particles we are talking about as electrons, which have negligible mass. That is why they have very low quality factor, given the magnitude of 1. Neutrons are much heavier compared to electrons, and therefore, they have certain quality factor, and that keeps on increasing with energy to become maximum around this 0.01 to 2 MeV level, and with further increase in this, further increase in the kinetic energy of the neutron, it keeps on decreasing the quality factor. Protons can have quality factor in this range depending upon two different classifications, and alpha particles are much heavier, because every alpha particle contains 2 protons and 2 neutrons. So, 4 times the mass of any individual proton or neutron, therefore, total damage it can cause is also much higher, and we have a quality factor of 20. The REM is therefore measured here, H is the REM, is measured as the RAD, which is D, into the quality factor. So, the total amount of energy that is getting deposited in the human tissue, what kind of reaction that is going to produce or response from the tissue, that depends upon the tissue itself and also on the nature of the energy or emitted radiation. Accordingly, we are defining this RAD and REM. So, if we combine all these units, the source activity from where the radiation is getting produced, that unit is Curie or Becquerel. Now, how much exposure in human tissue is subjected to, that is called Roentgen, which is given a measure of 2.5 into 10⁻⁴ coulomb per kg of air in kg of dry air at STP. Then we are talking about the absorbed dose measured in terms of RAD, and biological equivalent dose measured in terms of REM. Now, but RAD and REM, they are actually the useful units, but not SI units. Proper SI unit is Gray and Sievert. Now, 1 Gray corresponds to 100 rad, and as we know 1 rad is 0.01 joule per kg. So, 1 Gray is 100 rad, that is 100 into 0.01 joule per kg, that is 1 joule per kg, like this. Similarly, REM, biological equivalent dose is always the absorbed dose multiplied by the quality factor. So, if we are multiplying the absorbed dose given in terms of RAD with the quality factor, then we are getting REM, whereas when we are having the absorbed dose in terms of Gray, then we are multiplying that with the corresponding quality factor, we are getting Sievert. So, these two are corresponding to each other. Effective dose, different tissues and organs have different kinds of radiation sensitivity, different kinds of response. The equivalent dose can be manipulated by a factor often known as tissue weighing factor related to the risk for a particular tissue or organ to get effective dose absorbed by the body. and these are the tissue weighing factors. And you can clearly see some of the tissues are very much unaffected, or some of the organs like the bone surface is very less effect on this, or our skin a much smaller effect of radiation, whereas there are certain other organs where the effect is very strong. Like on the internal organ like colon, there can be very strong effect. On the stomach we can have very strong effect of radiation, and certain same on the lungs, they have very high this tissue weighing factor, and accordingly they are the most sensitive to this. Like bone marrow is another example of having 0.12 tissue weighing factor. So, these are very sensitive to any kind of radiation. Therefore, in a nutshell what we are trying to say is that just how much radiation you are exposed to, that alone does not matter, rather depends on two things. Firstly, from where the radiation is coming, what is the nature of this radiation, means the radiation is coming in the form of a gamma radiation or alpha radiation, accordingly its quality factor varies, and therefore, this biological equivalent dose can be viewed as like the potential for that radiation to cause some harm. And now this is going to fall on some particular organ, and the response of that organ is also not the same for all the organs. Some of the organs are highly sensitive, and some of the like the bone marrow or like the stomach, where certain organs like our skin are very less sensitive. Then we get something called the collective effective dose or population dose, where we take the entire population into consideration. It represents the total dose equivalent to a specified group of person. It is measured as the sum of all individual effective doses over the time period being considered. And if all the individuals are subjected to same kind of dose, then it will be just a product of the total number of persons into the number of dose received by per person. That is why it is often measured in terms of persons in sievert. Which is given like this, where n is the number of population, h is the corresponding dose, effective biological effective dose, which can vary from person to person, and infinity here refers to the total number of sample over which we are doing this, because in a population we can have infinite number of persons. In early 80s, the effect of background radiation was much larger. For medical instrument, it was only very small, only about 15%, whereas in 2006 the background has dropped to 50%, or actually it has not dropped, its quantity remains more or less the same or has increased a bit, but from medical part the radiation exposure has gone to very high level. It was about 0.8 million persons sievert, whereas it has become just in 20 odd years it has become 1.9 times person, 1.9 million persons sievert. This there are certain areas where the effective dose per individual is very high, like the Kerala coast of India has very high effective dose of radiation. Certain parts of China or US also has very high effective dose per individual. Now, this is an idea about what we are talking about, or rather I should say the biological dose that we just mentioned, we are trying to relate to different kinds of human activities. Like when you are having a typical chest X-ray, you are actually getting a dose equivalent to 0.01 millisievert, whereas when you are having a chest CT scan, it goes up to 7, and if you are going for even higher level, then we can have much higher level of radiation exposure. This is what the medical term that refers to. For different medical kind of examinations, we are still exposed to different kinds of radiation level. This is not small, this is a quite large dose, because if you compare this is 7 millisievert, and correspondingly the total annual dose received by a worker which is working in an uranium mine is only 1 millisievert for this in a certain part. Whereas when we are considering the nuclear workers working for 5 years in this, it can go up to 100 millisievert. So, several common activities like flying or certain medical examinations can still lead to some amount of radiation exposure. And there we define one final term, that is called the linear energy transfer, LET. Linear energy transfer is a measure of the interaction density along radiation travel path, means as the radiation is traveling, then how much interaction it can have with the surrounding medium. It is equivalent to the ionization potential or stopping power of body tissue. High LET particle deposits energy within a short interval of time, whereas low LET particle requires larger travel or longer time to lose its entire energy. It is inversely proportional to the radiation range, like short range particles like alpha have high LET. However, LET increases with increasing mass of the incident radiation, decreasing charge of incident radiation, and decreasing energy content of the incident radiation. In order of decreasing LET, if we express certain particles, then generally fission fragments are on or low mass number nuclei have very small LET, then it keeps on increasing with alpha particles, protons, etc., and high energy beta, X-ray and gamma radiations have much larger LET, means they need to travel much longer to deposit the entire energy. Whereas an alpha particle which is heavy and has a lots of energy content, it can lose all the energy within a short interaction time or short period of time. Generally, for particles having a LET of 3.5 or less, quality factor is about 1. Between 3.5 to 7, it is between 1 to 2. Between 23 to 53, it is 5 to 10, and greater than 53, it goes to 10 to 20. That is how we relate the quality factor to different kinds of particles. What are the sources of radiation then we are exposed to apart from the nuclear working? We get it from the irradiation coming from the sun, the external contamination or internal contamination coming through some of the foods that we are taking. See, this is a more common source, like suppose you have an water body and you have a surface deposit here where we have certain kind of or radioactive material stored. So, the water that is running off from there goes to the water body and can lead to the contamination or increase in the nuclear activity level for this water body. Then what are the things which gets directly contacted by the water body? The sands and sediments are there, aquatic plants directly taking it from the water body, and also aquatic animals. Now, when we are using those for our fooding, etc., then we are directly getting the corresponding radiation into our body. Also, original cloud of contaminated air can deposit it to the plants and crops, from where it can go to the animals or can go to the soil, which is subsequently used for production of foods and drinks. So, there are several ways we can get contaminated by radiation. Just what I talked about the medical thing. When you are doing an MRI, there is hardly any radiation exposure. However, if you are doing a simple head X-ray, then it is equivalent to 11 days of natural radiation exposure and 0.4 days of flying. Whereas, when you are having a head CT scan, it is equivalent to 1 full years of natural radiation exposure and more than 13 days of flying. So, that is a large dose of radiation that we are talking about. And finally, to relate that to the health hazard, we generally classify the effects of radiation into two categories. One is the stochastic effect, other is the deterministic effect. Deterministic effect refers to having a threshold or up to the threshold in terms of the magnitude of radiation or the quantity of radiation, there is hardly any effect. However, once the threshold is crossed, threshold is breached, then the effect starts increasing exponentially. Once the threshold is reached, then only it is going to happen, but beyond the threshold, the effect can increase extremely rapidly. Different effects tissues, people have different threshold doses for deterministic effect. All early effects and most normal tissue late effects are deterministic in nature. So, these are some numbers indicating the threshold for deterministic effect. Like in one single absorption, permanent infertility may happen for 3.5 to 6 sievert, whereas prolonged absorption sievert per year, it can be in the range of 2. The stochastic effect refers to no threshold. The increase is the likelihood as the dose keeps on increasing, the effect is more likely, but the severity of the effect is not related to the dose. It just indicates whether the effect is going to occur or not, but how much it is going to affect the subject, that it does not say. There is no dose above which the stochastic effects are certain to occur, and this includes the radiation carcinogenesis and hereditary effects. So, once a body is subjected to or a human tissue is subjected to different kinds of radiation or sustained period of radiation, then it can lead to the killing of our cells. The reproductive death of certain fraction of cell colonies when subjected to acute radiation. Like for high LET radiation, the survival fraction decreases very quickly within a short span of time, whereas it is much longer for low LET radiation. These are the different kinds of effects the human cell can undergo when subjected to radiation. Like 5 types of cell modification strategies are shown or possible cell modification like apoptosis, necrosis, sensation, autophagy and mitotic catastrophe. Each of them has their own reasons of occurrence, but always they lead to some permanent modification in the cell structure, or at least the cells which are in immediate vicinity of the affected area. The effect is even more stark for fetus, like within a gestational age of 0 to 2 weeks. If the threshold value is 50 to 100 milligray only, and the effect may not be any much significant. However, if between 2 to 8 weeks there may be congenital anomalies, growth retardation and childhood leukemia when it is being subjected to 200 or higher milligray amount of threshold. For 8 to 15 weeks, severe mental retardation, intellectual deficit and microcephaly, this kind of effects may appear. Then finally, between 16 to 25 weeks, severe mental retardation when it is exposed to a radiation greater than 250 to 280 milligray. So, that takes us towards the end of this particular module. I thought about discussing briefly about different kinds of pollution measuring instruments, but thought that is not going with this topic. So, there is just no point enhancing or extending this lecture just for the sake of it. So, in this module we have discussed about the acoustical measurements and we have discussed about radioactivity and biological effects of radiation. So, that takes us to the end of this course. I hope you have enjoyed it. There are different kinds of topics that we have discussed, wide variety of subjects that are included in this course, because though we are talking this as mechanical measurement, but we have used extensively used the concepts of electrical engineering, some concepts from electronics, certain times the concept of physics, and therefore, this is a very much I should say quite intricate, as at the same time very much involved part of any engineering discipline. Whatever is your observation, please keep on writing to me. I shall be happy to respond to your queries, and also any kind of criticisms I shall be happy to accept. Those who have registered for the examination, please go through all the assignments properly, because some of the questions will be coming directly from the assignment or will be inspired from the assignments, while some other questions will be a bit new to you. But I can ensure that the question papers will not be very tough. It is just a logical application of whatever we have discussed in this course, and so you should do well. So, at this particular point I would like to say goodbye for one final time, but if any of you need any kind of help, not only for this course, regarding any other topic also, I shall always be happy to be there. Thank you.